All right, so we're finally ready to talk about extrema of functions. So maxima, minima, whether that's local or absolute, just like we did in Calc 1. So if we have a function of two variables, and again, we'll narrow in on our conversation for functions of two variables, but the ideas will extend to functions of more variables. We say that f of x, y has a local max at some point AB if, well, f of AB is larger, greater than or equal to f of xy for all points xy, and I'm going to be a little bit imprecise here, in a small disk around AB. So I just mean for points really close to AB, the function value at AB is larger than any of those points. Okay, so let's look at a picture. Try to sketch this out. So here's our three-dimensional space, and let's say we have our point AB here. Then if we have a local max, what's going on is we're really looking at the top of a mountain. So here's f of AB up here. And then basically in any direction we look, in some small little disk like that, so here's my disk around AB, so I can find this small little disk, so all points xy, if I look at their image, it's smaller than this point AB. And in the back of your mind, you should just think top of mountain. And the same thing is true for local min. So basically, for a local min, we just want to switch this inequality. And instead of looking at the top of a mountain, we're going to be looking at the bottom of a valley in a small disk. So we have, again, our point AB. We have a small disk around AB. But then if we look at f of AB right here, then around this small disk, all of these function values are larger than f of AB. Okay, so it's very intuitive what we're talking about here for local extrema of functions of two variables. We have tops of mountain, and here we have the same kind of idea, except we're looking at bottom of valley. So we can also think about looking at these local extrema. So for now, we'll just say, without loss of generality, we're looking at a local maxima. The same will be true for a local minima. But we can actually look on the contour plot of the function. So here's actually the domain xy. So let's say again that f has a local max at this point AB. We want to sort of figure out a way to find this local max, or see whether or not f, or verify that f has the local max at AB. So let's put our point AB right here. So that's AB. And let's draw some level curves potentially of this function. So maybe we have something like that. And then we know that this local max is the top of a mountain. So this is where you can really think about your topographical maps. So the top of the mountain is going to be sort of circled in by these contours. So this is, these outer rings are going to be lower values of the function, and they're going to be increasing. Okay, but now let's think about the gradient for a second. Okay, so the gradient, recall, points in the direction of greatest change, but I'm just going to be a little bit informal and say it points uphill. So if I pick a point here, say, and I look at the gradient, then it's going to point that way. Or maybe I'm here, and I look at the gradient, it's pointing that way. I look here, the gradient's pointing that way. I look here, the gradient's pointing that way. I look here, the gradient's pointing that way, and so on. And so you see, I almost have this game I can play. I start at a point, and I say, all right, well, what is the gradient? Well, the gradient is positive, it's pointing me this way. I'm going to go that way. And then I can sort of trace out, so okay, I'm going to go this way, and then maybe I get here, and the gradient points me this way, and the gradient points me that way, and then that way. And when am I going to stop? Well, I'm going to stop exactly when there is no direction of greatest change. Or in other words, I know I have a local maximum if the gradient is 0. And of course I'm assuming that f is differentiable. So I'm assuming f is differentiable. But if f is differentiable in this domain, then my gradient's going to be positive, 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 or it's going to be pointing in the direction of greatest change until I get to the top of the mountain. And in the top of the mountain, I'm going to have a flat tangent plane, sort of like the idea in Calc 1 where we have a horizontal tangent at that point where we have a local max. Now exactly the same thing is going to be true for a local min, for exactly the same reasons. So what we see is that the gradient being 0 for a differentiable function is going to be necessary for f to have either a local max or local min. So just like in Calc 1, the derivative being 0 didn't guarantee that that point was a local max or a local min. But what it did give us is it gave us candidates to see whether or not points were local max or local min. And so what we need now that we know how to find some candidates to see where we have local extrema, we actually need a test to say, okay, this is a local max, this is a local min, this is neither, or maybe I don't know, and that's what we're going to talk about next. All right, so just a little bit of terminology, and this is all recycled actually from Calc 1. So a point in the plane AB is called a critical point of some function of two variables if, well, remember that a critical point of a function of one variable was an x value where the derivative was 0. Well, we have a slightly different notion of derivative. Our notion of derivative now is the gradient. So AB is a critical point if the gradient of f evaluated at AB is equal to 0. So I'll mention that actually from Calc 1, recall that a critical point was a point in the domain of f where the derivative was either 0 or undefined. And we can use this same idea here. So you can also call a critical point a point where either the partial with respect to x or the partial with respect to y is undefined. But we really just want to narrow in on the case where the gradient is 0, at least for now, just to keep things simple. Okay, so we have a critical point of our function f if the gradient is 0. Now, here comes what's called the second derivative test. For local extrema. So what we're going to do is we're going to let this point AB be a critical point of a function f of xy. So we know the gradient of this function evaluated at AB is 0. Now, we cannot say right off the bat that that's a local extrema, that it's a max or a min, but we have a test. So we want to define this sort of weird test function that we're going to call d of a b, or maybe just d for short if there's sort of no ambiguity about which point I'm talking about. So what is this? Well, it's going to be the second derivative with respect to x evaluated at AB times the second derivative with respect to y evaluated at AB minus, and now I'm going to make one more slight assumption that actually the mixed partials of f are equal, okay, which is okay. I mean, I'm already assuming that f is differentiable here, so I might as well go a little bit further. Okay, so I take one of the mixed partials evaluated at AB and square it. Okay, so I have this sort of d test function. So here is the deal. If, first thing, d is greater than 0 and f xx of AB is less than 0, then f of AB is a local max. Okay, secondly, if d is greater than 0 and f xx of AB is greater than 0, then f of AB is a local min. Okay. Now what about if d is less than 0? What does that mean? Then f of AB is a saddle point. And so specifically, it's not a local max or a local min. And similarly to a saddle point in a function of one variable, it looks like a saddle. And so you should look up a picture of what a saddle point is. And so it typically means in one direction we have a local max, and then in the other direction we have a local min. So we have some sort of inconsistency there. And then finally, what about if D is equal to 0? Then what do you think? Well, the test is inconclusive. So the test doesn't tell us anything. Okay. So again, if D is greater than 0, we just test the second derivative with respect to x, whether or not that's less than 0. This is sort of like concave down. This is like concave up. So local max, local min. So this is very much like the second derivative test for a function of one variable, but we need this D to be positive. And then D less than 0, f of b is what's called a saddle point, and then if D equals 0, it's inconclusive. Okay, so I just want to kind of wrap up a couple points about the second derivative test. So first of all, there's actually a way to think about the second derivative test that makes it a little bit easier to remember. So recall that this D of AB was defined in a certain way. Well, I actually want to give its definition in terms of a determinant. And now actually, there's kind of this interesting phenomenon that's happening. So if we have a scalar function of two variables, and we take the gradient, or somehow the first derivative, we end up with a vector. So it has two components, an x and a y component. Now, if you think about taking the second derivative of a function of two variables, well, what you're going to get is you're going to get a matrix, because I sort of have to put in all the different possibilities of taking the derivative. So the gradient was just a 2 by 2 matrix. I just had two choices. I could take the x derivative or the y derivative. The second derivative is somehow a matrix. So I just have all four possibilities of taking the derivative. Now we typically assume that these are the same under mild assumptions about f. But this matrix has a name. It's called the Hessian matrix. And now you don't really need to know that. But what's really useful is to realize that this D we were referring to is actually just the determinant of this matrix. So if you like cool ways to remember things, that's what this is. It's just the determinant of this 2 by 2 matrix consisting of the partial derivatives. And again, we typically assume these to be the same. And so when you do this times this minus this times this, it's this times this minus this squared. So that's just kind of a nice mnemonic to remember this test function for the second derivative, and it really is related to the second derivative of a function of more than one variable. It's related to this Hessian matrix. Okay, so the next thing I want to talk about is saddle points. So we talked about local max and local min. But what is a saddle point? Well, I'm going to give you an example just so you can kind of see the problem that's going on with a saddle point. And now there's sort of more than one type of saddle point. But let's just give an example. So let's say we have this point AB. And so somehow, if we have a local max, then if I look in the x direction, we'll have a local max, and I look in the y direction, we'll have a local max. So there's somehow a consistency in any direction that it's a local max, and same for a local min. Well, a saddle point happens basically when there's some inconsistency. So for instance, if I look along the x, or this will be the y direction, I have a local min, but then if I look in the x direction, I have a local max, like this. And so you can really start to see why you call it a saddle point, because in one direction you have local mins, in the other direction you have local max, and it sort of makes this nice saddle shape like that. So this is just an example of a saddle point, but we see that actually the gradient is going to be 0 at this point. Alrighty, so now that we've talked about local extrema, it's worthwhile to talk about absolute extrema. So remember, the difference between a local extrema, say a local maximum, and an absolute maximum is that a local maximum, we just sort of zoom in around that point, and it's a local maximum. But an absolute maximum means it's larger than any point in the entire domain of the function. So an absolute max, and I'm going to state this for a maximum, but the same is true for minimum if you just switch the inequality. So an absolute max of a function of two variables so we say it occurs at a point AB if f of AB is greater than or equal to f of xy for all points xy, not just in some small disk around AB, but for all points xy in the domain of f. So it's much stronger. So it's very much a global maxima. So I look at that point, and no matter where else I look on my function values, it is larger than all of those points. So recall, we also had a nice tool in Calc 1 called the extreme value theorem. And so we know that there are examples of functions of one variable that do not have absolute maxima or absolute minima. However, in the case that we were on a closed interval and the function was continuous, the extreme value theorem stated that the f would actually have an absolute max and an absolute min. And we also knew how to find those absolute maxima and absolute minima, and that was to find the critical points. And that the absolute max and absolute minima of a function would either occur at a critical point or on the boundary point. So that's the same thing here. So I'm going to state the exact analog of the extreme value theorem for functions of two variables. And again, this will extend to functions of three or more variables as well. So if f is continuous, and here we go. We're going to have to elaborate on this a little bit. But if it's continuous on a closed and bounded region, then the conclusion is exactly what we want. F attains an absolute maxima maximum, it's going to be unique, absolute maximum and absolute minimum. And so you should really just think about the one variable case that we want a function to be continuous on a closed interval. This is a little bit different, closed and bounded region. We're going to have to talk about what that means. But assuming we have these two things, then f will attain an absolute maximum and absolute minimum on this region. Okay, great. So let's talk about actually what a closed and bounded region is. Okay, so a closed and bounded region. So let me just say closed. What it basically means, it means that it contains its boundary. And so you can think about a closed interval contains its endpoints, its boundary points. And bounded simply means contained in a disk of finite radius. So somehow part of the region is not going off to infinity in some direction. So I think the best way to understand this is just to look at 3 examples. Okay, so let's look at a region that is closed and bounded. Okay, so that's going to be a function, a region that contains its boundary. So here's its boundary, so I'm including its boundary. I'm not drawing it dashed. And of course, contains everything in between. So that would be closed and bounded. So then we can also think about a region that's bounded, but not closed. Well, it's going to be a region, it still is going to be bounded, but I'm going to draw its boundary dashed, signifying that I'm not including its boundary. So it's a set, and the points on the boundary are not included. Like that. So it's sort of like an open interval, does not include its endpoints. But the boundary of a region is sort of a curve, so it doesn't include its boundary curve. Then we can also look at a region that is not bounded. And so somehow here, do something like this. So the boundary curve of the region goes off to infinity in some directions, and I'm looking at all of the points, going off to infinity. So there's no, I can't kind of circle it around with I can't pick a radius large enough for a disk to contain all of the region. It's kind of going off to infinity. So as long as our region is closed and bounded, and we have a continuous function defined on there, then we know by the extreme value theorem that the function will have an absolute maxima and an absolute minima. Okay, so before we do some examples, let me just sort of reiterate the strategy for finding absolute extrema. So suppose we have f continuous, and then it's defined on a closed and bounded region, like this. So domain looks something like this. So here I'm just drawing a closed and bounded rectangle, something like that. Or it could be a triangle, or it could be any shape as long as it's bounded. So it just is, right there in the plane, not going off to infinity, and then it contains its boundary. Okay, so the strategy is that, all right, well, first of all, I know the absolute max and absolute min occur somewhere in this region. And so what I first want to do is find the critical points. So I want to set the gradient equal to 0. And that's going to give me some points inside the region that my absolute max and absolute min could potentially occur at. Okay, so I want to test the values of the functions at these critical points. Okay, so find critical points. Okay, but what do I do next? Well, I have to test the boundary. So next, test boundary. So what I do, so here I have 4 boundary components. I have this component, I have this component, and I have this component. So I want to test the boundary individually. So what I'm going to do is I'm going to look first at this boundary component here. And now what I'm going to view this as is I'm going to cut the function here and look at the function as a function of one variable on this little piece of line. Maybe this is like the line y equals 2. So I'll just set y to be 2 and I'll get a function of x. And then I find this is a closed interval. It's going to be a continuous function. So I want to pick up my endpoints and I want to find any critical points of this function on the boundary. And then I want to do the same thing on this piece. I have another, if I kind of cut the function here, I have a continuous function of one variable on this little closed interval. So I find the critical points and the endpoints. I do the same thing here and here. So I test boundary critical points by plugging them into the function. As well as the endpoints. So I want to test these points, and then I want to test the boundary critical points and the boundary endpoints. And I know that one of those points is going to be where the absolute maximum occurs, and one of those points is going to be where the absolute minimum occurs. And so I just need to test them all, find the largest, find the smallest, and I'm done. But it's a little bit more involved because you can see even with this square region, I have to find where the gradient is 0, but it also somehow reduces to 4 one variable optimization problems. So these problems can be a little bit involved. Yeah, I'm not going to deny that, but that's the basic idea. It's sort of straightforward at its heart. All right, so we want to find the critical points of this function. And recall that the critical points of a function of 2 variables are the points x, y, where the gradient is equal to 0. Or in other words, well, this is a vector equaling 0, and now here I really mean like the 0 vector. So this happens exactly when the partial with respect to x is 0 and the partial with respect to y is equal to 0. Okay, so what is the partial with respect to x? Well, it's going to be 2x e to the x squared plus y squared, and then fy is 2y e to the x squared plus y squared. Okay, so if I set these equal to 0, what is the only way that both of these are going to be 0 simultaneously? Well, this exponential is always positive. So the only way this is going to be 0 if x is 0. And the only way this is going to be 0 is if y is 0. So the only critical point is going to be the origin. 0, 0. All right, so we want to find the local maxima, local minima, and then any saddle points of this function. F of xy is x squared plus y squared x plus 4. And now recall that our candidates for local extrema, or saddle points for that matter, are the points where the gradient is equal to 0. AKA, we want to find the critical points first. And so recall that what I really mean by saying the gradient of f is equal to 0 is that the gradient vector is 0. So that happens exactly when the partial with respect to x is 0 and the partial with respect to y is 0. So what's the partial with respect to x? Well, that's going to be 2x plus y squared, and I'll set that equal to 0. And then the partial with respect to y is 2y plus 2yx, and I'll set that equal to 0. So this is something that's going to play a central role, here and also in the next topic, solving systems of equations like this. So we want to be really careful and kind of do some factoring and look case by case. So what we have here, if I factor out a 2y, I have 2y and then 1 plus x is 0. So here, either y is 0 or x is negative 1. So if y is 0, well then if I plug in 0 for y, I have 2x is 0. Well, that means that x is 0. And then what about if x is equal to negative 1? Well, I plug in negative 1 for x, and I'll add over 2, and so I'll have y squared is equal to 2. So then I have y is equal to plus or minus square root of 2. Okay, so my critical points are going to be 0, 0, and then minus 1, and then plus or minus root 2 for y. Okay, so now what I want to do next is actually find this test function d. And so in order to do that, I need to find the remaining partial derivatives. So the second partial derivatives. So I need fxx. Well, that's going to be the derivative of this, so that's just going to be 2. And then fyy is going to be 2 plus 2x. And then fxy will be the same thing as fyx, which is 2y. And so if I evaluate at, say, 0, 0, and remember that this d function, let me write it up here, or down here, so d is going to be fxx times fyy minus fxy squared. So I'm just going to take this function and evaluate it at 0. So that's going to be 2 times 2 minus 0, so it's going to be 4, which is greater than 0. So that tells me I either have a local max or a local min. And now because fxx of 0, 0 is 2, which is greater than 0, I can conclude that f of 0, 0, which is 4, is a local min by my second derivative test. So my d at 0, 0 is positive. My second derivative of x evaluated at 0, 0 is positive. So this point is where a local min occurs, and that local min is actually 4. Okay, and then now let's do the same thing for -1 plus or minus root 2. Now I'm doing this because we'll see that actually the same thing will happen. So if I take fxx, fyy, fxx is 2, fyy is 2 plus 2 times -1, which is 0. And then what do I do next? Well, okay, so that's going to be 0 minus, if I plug in plus or minus root 2 in for y, here, I'm going to have a number squared, so this is going to be, well, in both cases, so it's going to be 4 times 2, so it's going to be 8, so -8, sorry. So again, that's coming from, if I plug in root 2 or minus root 2, here, that's going to be 8 when I square it, but I'm subtracting it. So this was 0, and then I subtract, I get -8, which is less than 0, which means I have saddle points, so -1 plus or minus root 2 are saddle points. Okay, and that's it. So I have one local minima here at 4, and I have 2 saddle points at -1 plus or minus root 2. Okay, so we have this function, and we have this domain. And now what is this domain? Well, it's going to be a rectangle. And notice that it is indeed closed and bounded. And also that this function is continuous. So what that means is that we know we're going to have an absolute maxima, an absolute minima on our domain, which I will draw as such. Okay. And so the first thing we want to do is find any critical points. So we will find the critical points. Find critical points. And remember, all we're really doing here is finding a list of points that potentially could be where the absolute max and absolute min occur, and then evaluate at all those points, pick the largest, and pick the smallest. Okay, so first we're going to find the critical points of f. So in other words, I want to set the gradient of f equal to 0. So in other words, I want fx, which is just going to be y plus 2x, to be 0. And then I want fy, which is just going to be x, to be 0. Okay, so notice, let's see, y plus 2x, and then fy, it's just x, good. So notice that x is 0, and then if x is 0, we're going to have y as 0. So our only critical point is the point 0, 0. Okay, that was pretty straightforward. So now, there's our critical point. There's one point we'll have to check, 0, 0. So now we need to actually look at 4 different regions. So we'll just kind of section them off here. Okay, so what are these 4 regions? So up here, we have y equals 2. Down here we have y equals -2. That's our other boundary component. We have x is 2 on the right-hand side, and we have x is -2 on the left-hand side, like that. So we'll look first at y equals 2, y equals -2. We'll look at x equals 2. We'll look at x equals -2. And so what I'm going to do is I'm just going to find the function of one variable on all of these boundary components. So first of all, if y is 2, well, I'm looking at the function what? So looking at x comma 2, which is 2x plus x squared. Okay, and then this is just a function of one variable, and now x is going to be between -2 and 2. Over here, when y is -2, I'm going to have -2 well, this is going to be -2x plus x squared. And then over here, we're going to have f of 2y, which is just going to be y, 2y. X is 2, so 2y plus 4. And then over here, we have f of -2y, which is going to be -2y plus 4. And so now I'm looking for the critical points of these functions. So I want to take the derivative. So here, f prime is going to be 2 plus 2x. And I want to set that equal to 0. Well, that's going to happen when x is -1. So I get another critical point of -1, 2. And that actually is in our domain. So -1, 2. It's up here. It's another point we need to check. Over here, if I take f prime, that's going to be -2 plus 2x. And if I set that equal to 0, well, I'm going to get x is equal to 1. So I need to check also the point 1. 1, -2. Which is down here. Okay, and so notice for these two functions, when x is 2 and x is -2, we're not going to have any critical points because the derivative is never 0. Here it's just 2, here it's -2. Okay, but I also need to test the endpoints of all of these intervals. Here, here, and here. So I have 1, 2, 3, 4, 5, 6, 7 points to test to find where my absolute max and absolute min occurs. So let's get to work. Let's test 0, 0. Well, that's 0. Let's test, what else? 2, -2. So what is that going to be? So that's going to be a, let's see, -4 plus 4, so that's going to be 0. I think that's also equal to f of -2, comma 2. So those will both be 0 because I'll have a -4 here, and no matter what x is plus or minus 2, it's going to be square roots of 4 there. So we can also look at f(2), and I think this is actually going to be the same thing as f (2), (2), which is going to be 8, right? So 2 times 2 is 4, or -2 times -2 is 4. plus 4 is 8. Okay, and then if we look at, what are the other two? Negative 1, 2. Well, we're going to have negative 2 plus 1. Negative 2 plus 1. And then also the same thing over here. So this is actually going to be equal to f of 1, negative 2 is going to be negative 1. Okay, but now we can just read off what our absolute max and min are. So here is our absolute max. And then here is our absolute min. Absolute max is 8. Absolute min is negative 1. And you can see exactly where the absolute max and the absolute min occur. Okay, so we want to find the absolute max and absolute min of this function, which is continuous, and is also defined on a closed interval. So let's sketch this closed interval, or sorry, not closed interval, the closed and bounded region. So let's sketch the closed and bounded region on which this function is defined. So it's basically inside the unit circle, including the boundary of the unit circle. Alrighty. So what do we do? Well, we start by finding the critical points of our function f contained in this region. So those are the points where the gradient of f is 0. Alright, now where is the gradient of f 0? So that's where f of x is 0 and f of y is 0. So what is f of x? Well, we got to do a little bit of quotient rule here. So we have a negative 2x divided by this other function of x. So we'll start with the bottom. So x squared plus y squared plus 1 times the derivative of the top minus the top times the derivative of the bottom with respect to x, so that's just 2x, and then all over the bottom squared. And now if I set this equal to 0, I really just want the numerator to be 0. And so what is the numerator? Well, I have definitely a factor of negative 2 I can factor out. And so let me just solve for this numerator. So I have negative 2 times, well, I have x squared plus y squared plus 1. And then this is, I factor out a minus 2x, but I have another minus 2x squared is 0. Or in other words, minus 2 times minus x squared plus y squared plus 1 equals 0. So that's just the partial with respect to x, and I've set it equal to 0. If I take the partial with respect to y, well, I'm going to get something really similar. So the partial with respect to y is going to be, well, here I'm going to have to use a little bit of chain rule. So I'm going to get something like 4xy, because I'll multiply the top by 2y, all over, and I also multiply by negative 1, x squared plus y squared plus 1 squared. So again, if I set this equal to 0, I just want 4xy to be 0. So either x is 0, in which case if x is 0, well, I have y squared plus 1. That's never going to be 0. So actually, this is impossible. So if x is 0, I look up here, I need this equation to be 0, but if x is 0, this is always going to be positive. This is just going to make it negative, so that's never going to be 0. But if y is 0, then this factor can be 0 when x is plus or minus 1. So my critical points are 0, not 0, plus or minus 1, 0, which are here, actually on the boundary. There and there. So I need to check those 2 points. So there are actually no critical points inside the boundary. So on the boundary, what do? Well, I have that x is cosine theta, y is sine theta, x squared plus y squared is equal to 1. So what is my function? So f on the boundary, well, x is cosine theta, x squared plus y squared is 1, plus 1 is 2, that cancels with that 2, so I just have a minus cosine theta. And if I take the derivative, well, I have negative sine theta. Setting this equal to 0, well, I get exactly theta is 0 or pi. And of course, that's periodic, but it's exactly at these points. So again, the only critical point, not only do I have these 2 critical points on the boundary, they're the only 2 critical points on the boundary. Okay, so then what I need to do, I just need to test the only 2 possible points where the absolute max and absolute min can occur. So f of 1, 0 is going to be -2 over, this is going to be 1 plus 1, so 2, so -2 over 2. That's going to be -1, and then f of -1, 0, that's going to be -2 times -1, which is 2, again over 2, it's going to be 1. So we see we have our absolute max and our absolute min.